Welcome to our second week of point-of-care ultrasound instruction for physicians and practitioners. Thank you guys for coming back for another round of this. Today we're going to delve right into the physics of our ultrasound and modes of operation, which I hope you will find very useful. Even if it can be a little bit of boring and redundant, hopefully you will find the purpose of this and be able to utilize it to be more competent in your scanning and thus be able to effectively make your diagnoses. So objectives for today is to describe how ultrasound utilizes sound to visualize internal organs, compare and contrast ultrasound to other diagnostic imaging modalities, evaluate how and why high-frequency transducers produce high-resolution images but cause reduced penetration, and then differentiate between alternative imaging modes such as B mode, M mode, color, and spectral Doppler. Levels of sound, so if these are basic terminology notes here, but if we refer to infrasound, that would be inferior to the frequency in which humans can hear. So less than 20 hertz or less than 20 cycles per second of sound would be categorized as infrasound. Ultrasound, on the other hand, is going to be greater than 20,000 kilohertz or 20 kilohertz or 20,000 hertz. Frequency sound will be above what the human hearing can detect. So thus leaving human hearing at the level of 20 hertz to 20,000 hertz. And so what we are going to be utilizing and talking about here is going to be our ultrasound in the general region above 20,000 hertz, and we're typically going to be operating in the megahertz. One of the important concepts to look at is imaging principles. Now, imaging principles are the principles on which obtaining or acquiring your images are based. So currently there are two different types of imaging principles, imaging principle 1 and principle 2. The one that we are utilizing in the clinical field is typically principle 1. This is the more traditional principle that we'll talk about throughout this course. Just be familiar and aware that there is a principle 2. Now, if you're going to some of your medical conferences and different things, you might see images produced in principle 2 that far outshine what you're getting in your systems. Please realize that principle 2 is not utilized in most imaging systems at this point. They are fantastic, amazing images, but it's not that you're doing something wrong if you're getting a different type of image. It's more likely that you have principle 1, and so you're working within that particular realm. If we look at principle 1, it's still the most commonly used, and the idea behind principle 1 is that your transducer, or each part of your transducer, is going to emit one sound wave, wait and listen for the echoes back from that sound wave before it produces or releases another sound wave. So if we have a transducer that looks something like this, a little element here is going to produce a sound wave, wait for that sound wave to echo back, and then that particular element would produce a single imaging line like you might see up over here. Okay, now obviously we don't have one element working at a time in this principle 1. We have many elements across the top of our transducer here that are working together to produce numerous scan lines and create our image. So the basics of principle 1 is that sound is emitted by each element on the transducer as a pulse. When that pulse comes out, it's emitted into the tissue, and then that transducer goes into listening time. That listening time will allow for the echoes back from that sound wave to be received. When those echoes coming back from that scan line are received, their strength of echo is going to determine the brightness, and the time in which that sound wave was gone for before returning is going to determine the depth. So that is the whole idea behind our principle 1. Obviously, that's kind of a simplified presentation, but that kind of gets you started. So as we talk about principle 1, it's important to note the important components of our imaging transducer. So transducer, as you all know, I'm sure, is the name for the probe in which we hold in our hand while we scan our patient. That transducer can be a number of different shapes, as we'll talk about here shortly, but the idea that's similar to all of our transducers is that the transducer consists of a number of different crystals or elements, and each of these crystals or elements operates off of that principle 1, where each element is able to produce a sound wave and listen for an echo, collecting information to then go apply to the image. So each of these elements that we see here can be called an element or a crystal. They are made of some man-made composite material called lead zirconate titanate, or PZT. Now these elements have something called piezoelectric properties, and a piezoelectric property is basically falls under the idea that if I have a piezoelectric material and I have a voltage and I apply that voltage to the piezoelectric material, it is going to expand and then contract. And as it expands and contracts, it disrupts the media around it and produces a mechanical or sound wave. So when we are trying to emit sound into a patient's body, we're going to be applying an electrical voltage to these elements, causing that element, because of its piezoelectric qualities, to expand and contract. As it does this, it produces a sound wave that can move through a media. Now, sound waves are mechanical waves. They cannot move if there's no media present, meaning if there's a vacuum, there will be no sound wave. But since the body is made of a lot of soft tissues, we're actually really good at propagating sound waves. Now, on the other hand, this works really well on the receiving end as well. So what we talked about was the emission end, or the transmission end. Now we can talk about the receiving end. So as that sound goes down into the patient's body, it's going to be interacting with different soft tissues or bony tissues. And when that sound hits a particular tissue, oftentimes some of the sound will proceed and other parts of the sound will be returned as an echo. So when that sound returns as an echo, that sound property is going to act on this piezoelectric element, causing it now to expand and contract again, and it will then have an output of a voltage that correlates with the incoming echo. So it really works as basically the transition point of voltage to sound and then sound back to voltage. The frequency now of the voltage is really going to play a large role in the frequency of the sound wave created. So if you're not already familiar with this, you'll find out that higher frequency sound waves get attenuated or absorbed in the body more. So if we have a nice skinny little patient, or we're scanning something very superficial like a thyroid or a carotid, my sound wave can go in. Even if it's high frequency, it will make it to the back field and it will be able to come back and provide some diagnostic information to our transducer. Now, on the other hand, if I have a rather large, beefy patient and I have my transducer on them, if I use a high frequency sound wave, it's going to get absorbed in that patient and I won't have anything returning as an echo from which to create my image. So the frequency that we're using in our transducers is going to be essential. If you're having difficulty scanning a patient and you feel like your beam is just dropping out as it goes into the far field or deeper into your patient, it's probably a frequency issue. If we have an increase in frequency, we typically get much better resolution or much better presentation of what the anatomy that exists in the body really looks like. However, with that increase in frequency, we also get a huge decrease in penetration. So you might ask yourself, well, okay, that's great to know, but what do we do about it? Well, most of our equipment has options in where we can adjust our frequency. Some of those are very direct, where we can go to a button and it'll say frequency 3, 4, 5, and we can select our frequency as megahertz right there on that system. Other systems, however, may have more indirect control of your frequency, where you can tell your system, I want to penetrate. It would automatically drop down your frequency. Or I want higher resolution. It would increase your frequency. The way in which your equipment is making that happen is it's at that piezoelectric element level. So if I have a transducer that's capable of producing frequencies, say from 3 megahertz to 5 megahertz, depending on the voltage that I provide to that piezoelectric element here, will determine the frequency of my sound wave emitted into my patient. So you as the operator have control over some of that. And what it really comes down to is you do the settings. When you set the settings, the system adjusts the voltage, and the voltage should then correspond to the frequency of the sound wave that you're going for. Now, another term that you might see frequently is fundamental frequencies. So as I mentioned, many transducers, your basic curvilinear transducer that you might use for a AAA screening, that's going to range from usually about 3 to 5 megahertz. And because of that, that would be considered the fundamental frequency. If I have a 3 to 5 megahertz transducer, I'm operating at its highest frequency as a 5. My transducer's fundamental frequency would be a 5. Now, I'm not sure if any of you are like this, if we have any kind of physics nerds out there. I love the physics of sonography. But even if you don't love the physics of sonography, having a general understanding of it is going to be very important, and it's going to allow you to better operate your image, which will lead to better diagnoses. So when we talk about sound on the most basic principles, sound operates as a mechanical wavelength, meaning that it has to transverse through a material in order to exist. And when we look at how sound transverses through a material, we're going to be able to assess it for different qualities. So one of the qualities we look at is frequency. And if I wanted to define frequency, I would say that's the number of full cycles per second. So if this is our 0 point, and we're looking for positive deviation and negative deviation and back to the 0 point as one full cycle, this would represent a single cycle of a sound wave. Now, if I want to calculate the frequency of sound waves, it would be how many cycles per second occur. So when I'm looking at something, a probe that's operating as a 5 megahertz frequency, that would be 5 million cycles per second, therefore many, many, many different cycles coming out of that transducer in 1 second. Kind of fascinating to think of how quickly that operation of that system has to work to make that happen. Secondly, when we're looking at our sound waves, our frequency, if our frequency is known for telling us how many cycles per second, the wavelength then is known for telling us the distance that cycle takes up in space. So the fewer cycles I have per second, or the less my frequency, the longer my wavelength is able to become. So if I have a decrease in frequency, I have an increase in wavelength. And vice versa. If I am able to shrink my wavelength, making it much smaller, I'm going to be able to accomplish many more cycles per second to increase my frequency. Now, on another note, that's looking at, with my x-axis here, that's when we're talking about wavelength, that x-axis is representing distance. If we simply switched out the idea of distance on my x-axis and replaced it with time, that would describe my period. The period of sound occurs from the time it takes for one complete cycle to occur. So as I decrease my frequency, I increase my wavelength, I would also increase my period. So frequency and wavelength are inversely related. Wavelength and period are directly related. Now, amplitude is another quality of your sound, and amplitude is basically the deviation from the baseline to the maximum value. Amplitude is going to play a big role in that when we send sound into a body, that sound goes into that body, it's going to interact with different tissue interfaces as it goes through. Usually those tissue interfaces are not going to reflect the entire sound wave, but rather reflect parts of the sound wave and lets other parts of the sound wave continue. As we have some sound waves reflected, the amplitude or the intensity of the remaining sound waves up here is going to decrease. So that's something we watch very close. If we look just one more step into these sound waves and we apply it to how they operate within the body, it's important to understand that as the sound waves transverses through a patient's body, what's happening is it's causing molecular motion or an atomic motion within the patient. So as my sound wave goes through my patient's body, these areas peak will cause the molecules of that patient to compress, and then as that wavelength moves through and deviates to the other direction, it will allow the molecules to then expand. Because of that, we look at these areas of compression and refraction within patient tissue. So when they refer to the acoustic variables, it's really defining areas of increased pressure or decreased pressure, areas of increased density or decreased density, and areas of particle motion moving from compressed areas to refracted areas. Now, this consideration comes into play more when we start talking about another option with our sonography units called harmonic imaging. And so some of this will kind of get tied together when we get to that point. This is just a basic review slide over what we just talked about, but our frequency, like we mentioned, is cycles of second, showing complete forward motion deviation, complete backward motion deviation back to its original starting point. That would be one wavelength. The number of those cycles per second is going to determine our frequency, and 1 cycle per second would be represented as 1 hertz. So when we're looking at megahertz, we're talking about millions of cycles per second. Okay, and then wavelength, we're going to express that wavelength in millimeters. Our period, we're really usually expressing in, I'm sorry, I have a meter here, and that should be a second. So this should be, period should be expressed in microseconds. I apologize for that. And then the amplitude, like I said, is the deviation from the baseline. That's going to be affected by how much of that sound is being absorbed within the body before an echo is returned back to the transducer. Now, another important quality of sound when it's within the patient is propagation speeds. So sound will travel through every different type of material at a different propagation speed. Now, you might think of your soft tissue in your abdomen as having all one particular propagation speed, but every molecule is really going to have its own propagation speed. And so to determine an overall general propagation speed or speed of sound travel through the body, they really do an average. So the average propagation speed for soft tissue is 1540 meters per second or 1.54 millimeters per microsecond. Now, the reason this is important is because a change in tissue propagation speed, so as you're going, say, from the lung to the diaphragm, the lung and the diaphragm are going to have very different propagation speeds. And when you are transmitting through 2 different tissues with very different propagation speeds, you're going to get huge echoes back. So an example of this might be is if you are evaluating the thyroid and all of a sudden you see this big dropout behind the thyroid. Well, the trachea lies behind the thyroid, and oftentimes you're going to be sending sound through the soft tissue of the thyroid, moving at 1540 meters per second. That sound is going to reach the trachea, which is filled with air and has a propagation speed of only 330 meters per second. And because of that significant change in propagation speeds, all of your sound wave is going to get echoed back, so you're not going to be able to penetrate into that trachea well. So understanding how propagation speeds work, what tissues, what materials have variable propagation speeds can help you really utilize your ultrasound more effectively and identify areas where ultrasound may not be your approach of choice. Now, what determines our propagation speed? Well, it's going to be the density and stiffness of a medium. And if you go back to your basic biology, we know that the more dense molecules are packed, more typically we're going to have a stiffer material than if we have very loosely packed molecules. And so in our areas of increased density and stiffness of a medium, like say bone, we're going to have much higher propagation speeds. If we have very loosely packed or very soft materials, such as say fat, we're going to end up with much lower propagation speeds. And if we have even looser packed molecules, such as air or other gases, we're going to have even lower propagation speeds. So the propagation speeds are the speeds at which sound is traveling through a particular material. any change in those propagation speed will create an echo. Now, as I mentioned with principle one, we said that we have a transducer and we're emitting a sound pulse. We're waiting for that pulse to transmit through tissue, echo off of multiple anatomical components, and then return back and be read by the transducer. Now, because of that, we do not emit sound continuously. We emit our sound in very small pulses with a pulse and a listening time, a pulse and a listening time. So because that is how in medical imaging or diagnostic sonography we're utilizing ultrasound, it's important to understand a few terms that go along with that. So if I have many, many pulses being created per second, I am going to have a high pulse repetition frequency. Very similar from the descriptors we already talked about. Now, if I have a pulse and I want to know how long it is from the beginning of that pulse to the beginning of the next pulse, that would be my pulse repetition period. If I want to know how long it takes for my one pulse to be created before I can start listening, that would be my pulse duration, or the time it takes to complete one pulse. If I wanted to find out exactly how hard my transducer is working, and this component comes in very important when we start looking at the bioeffects of ultrasound, if I want to see how hard my transducer is working, I would check its duty factor. The duty factor is the percentage of time that the transducer is emitting sound waves. So if I was emitting sound waves the whole time, then my duty factor would be 100% or 1. However, in this instance, if I'm only creating sound waves about 50% of the time, my duty factor would be 50% or 0.5. Now, really, when we're looking at diagnostic ultrasound using principle 1, most of the duty factors are 0.1 to 1%, which I find very reassuring. When I'm scanning patients, I know that only about 1% of the time am I actually exposing them to any sound waves. The rest of the time is really made up by this listening period. Okay, another term that you want to be somewhat familiar with, because this is actually going to contribute to what we call axial resolution. The term is spatial pulse length. So if I look here and I said, okay, if each of my cycles takes up this much space and time, the wavelength takes up such and such space, and I want to know how much space the overall pulse takes up, I would multiply my wavelength times the number of cycles in my pulse, and that would give me my spatial pulse length. Now, why is this important? The smaller your pulse is that's going down into patient tissue, the more easily it's able to interact with objects that are arranged anterior to posterior. So if I have a very small spatial pulse length, it is much more likely that my pulse will fit in between these two objects, become echoed, and bring about sound or information from between the two objects. And if it's able to do that, it is going to be able to display or represent those two objects as two separate entities on my image. Now, if I have a very long spatial pulse length, it's going to be too large to interact with any tissues in between these two items, and it would therefore represent the two items as one mass. Now, because of this, this would be poor resolution. So when you understand spatial pulse length, it's important to know that that's another thing that you as the operator can try to adjust to optimize the resolution or your ability to see things that exist between the front and the back of your screen. Okay. Next and lastly is bandwidth. So I had mentioned that if we were using a common transducer for abdomen scanning, which would be a 3 to 5 megahertz transducer, that would tell me that this transducer is not capable of only producing one fundamental frequency. It can produce multiple different fundamental frequencies. And because it has a variety of frequencies it can produce, that variety is really referred to as the bandwidth. So here is a graph that demonstrates or gives a little further explanation of what bandwidth is. If my fundamental frequency was a 2.5 to a 6.5, I have all of those options and I could image at any frequency in between. My bandwidth would be the difference between 6.5 to 2.5, or a bandwidth of 4. Now, if I had a very narrow bandwidth, let's say my system could only operate at a 5 to 7. That would be a much narrower bandwidth. I'd only have a bandwidth of 2, which would give me less flexibility in the frequencies I could use with that transducer. So especially for some of those of you that might end up shopping for your own equipment, purchasing your own equipment, you want to be familiar with what bandwidth is and with how that affects your ability to change operations to image your patients better. Now, I did mention briefly how when we look at how the sound propagates through soft tissue, we have areas of compression and areas of refraction. Compression increases the density of my molecules. Areas of refraction allows them to spread back out. Now, what they found is as we introduce sound to the soft tissues and we get these areas of density, we know that propagation speeds, which we refer to as C, the propagation speeds in soft tissue increase if we have an increase in density. And we kind of talked about that when we talked about the overall propagation speeds. So as we see that we're emitting a certain frequency of sound into the body, we see that as that sound transmits through the body, it compresses molecules. As those molecules compress, they become more dense. And as they become more dense, they become more stiff, and the speed or the propagation speed in that area is thus increased. So what we see is when we start to scan a patient with, say, a 5 megahertz transducer, once that sound gets into the body, we actually end up with additional frequencies. So we call those frequencies harmonics. So if I'm scanning with a 5 megahertz transducer and I know as sound propagates through that body, I'm going to get faster and faster frequencies, my system is actually going to be operating at multiples of that operating frequency. So my frequency I might be actually getting back could be multiples of 5. So as I'm putting 5 megahertz in my patient, we may actually be receiving signal at 10 megahertz, 15 megahertz, so on and so forth. Those additional frequencies that are generated within the patient are referred to as harmonics. Now, a lot of people really appreciate harmonics because one of the things we just had talked about is if I have a higher frequency, I have better resolution. So harmonics allows us to put a lower frequency into the patient so that we're still getting some of that lower frequency feedback with its associated penetration, and yet we're still getting some harmonics back with the higher frequency to give us some improved resolution. So the combination of those two things can really make a significant impact on our images. Now, in the event that you have harmonics on, which most systems will allow you to turn it on and turn it off, in the event that you have it on and you're not seeing well, it is never wrong to turn it off and see if that improves your image, and vice versa. So this is another scanning option that can really impact your ability to assess tissue in the patient body, and I highly recommend you play with this to see certain areas where you like harmonics on and harmonics off. I know for one, in my scanning, if I'm scanning a fetal heart, oftentimes I'll want harmonics off. Whereas if I'm scanning an adult gallbladder, I'll definitely usually want it on because it helps reduce artifacts. So one of those things that you want to play with quite a bit until you identify your preferences. So I briefly mentioned how important it is to understand how a sound is interacting in the body. And as we discussed, we have the transducer, it emits a sound pulse goes into the patient's body, interacts with tissues of different propagation speeds, and as those propagation speeds change, it's going to cause reflection. So as the sound penetrates through the body, the amplitude of those sound waves is going to decrease as the sound penetrates deeper and deeper. When we look at it, how that amplitude decreases, as you see in this illustration here, we can describe the extent of that decrease by decibels. And when I teach my sonography students about decibels, you guys might be much more familiar with these, but decibels just really refer to a change in intensity. So a lot of music, we work off of decibels. So if we're turned down to basically nothing, that would be 0 decibels. And as we turn it way up in volume, that would be a positive decibel change. If we're looking at it on the attenuation end within the body, we actually have a significant negative decibel change because we have a decrease in amplitude as it penetrates through the body. Now that decrease in amplitude is caused because the interactions of the sound waves within different materials of the body, as I mentioned. So as my sound wave comes in, it hits a media with a new propagation speed. Some of that sound is going to be reflected. Some of that sound may interact with that and be absorbed in a way where that sound is transferred to heat. And then other can be reflected out in a non-accurate direction, which would be considered scatter. So because our incoming sound wave gets through that media with a lesser amplitude than it came in at, we would say that that sound wave has been attenuated. And the 3 ways it's been attenuated is because absorption, where it's converted to heat, reflection, where it's echoed back to the transducer to create an intensity on our image, or scattered, where it's emitted in an inaccurate angle. So because of attenuation, the reason this is so important is because of attenuation, it's really going to limit the depth or ability to penetrate through a patient. And so understanding how to manipulate this to reduce attenuation can be very helpful when it comes to your scanning practices. So if we look at exactly what attenuation looks like in the sonography realm, it really is significant. So we have a decibel increase every centimeter of tissue that we go through. So if this is my patient's abdomen, for every additional centimeter, we're going to have a significant decibel increase. The way we know what our decibel increase will be is through a calculation where we multiply our fundamental frequency, so whatever frequency we're telling our transducer to use. So if I have a 5 megahertz transducer, it's 5, and I'm operating at a 5 megahertz, its fundamental frequency is 5. If I want to know how much of that sound is going to be absorbed per centimeter of patient, I would multiply 5 times 0.5. That would tell me that my decibel of attenuation per centimeter is 2.5 decibels per centimeter of attenuation. Now, the interesting thing here is if you were to consider what a 12 megahertz transducer, which is common to our linear transducers for carotids and thyroids and things like that, our 12 megahertz transducer, if we divided that 12 megahertz by 5, we would have 6 decibels of sound attenuation per centimeter. Now, the reason that is so important is if we look at what a change in 6 decibels is, a change in 3 decibels, so say if I'm using a 5 megahertz transducer, we decided that that would give us a 2.5 decibel decrease per centimeter. Well, if I start out with 100 watts of power or amplitude coming into my patient, and after it has traveled only 1 centimeter in my patient, almost 3 decibels of that sound is going to be gone. If we look at what 3 decibel reduction really means, is it means half of our sound is going to be gone. So for every additional centimeter, we're going to reduce the existing intensity by another half. And that's kind of a good demonstration on how your sound gets eaten up so quickly in especially your thicker patients, and why, for example, if we're using that 12 megahertz linear probe, which would result in a 6 decibel per centimeter reduction, we would lose 75% of our intensity after every single centimeter. We'd move 75% here, another 75% there, so on and so forth. So this is just a good example of why that theory that we're taught about higher frequency means lower penetration, why that is so important in your scanning. So if you know that, trying to reduce the depth that you're scanning is going to reduce the attenuation, which will leave you more remaining beam to produce an image. Some of the ways that we can do that is if I have, say, a kidney, and I would have to, going through the anterior part of the patient, I would have to go through a significant amount of tissue. But coming over here and scanning through a window of their ribs, I would have to go through half that much tissue. Thus, my attenuation would be better, and I would get a lot more beam to interact with my kidney to improve my visualization. So those kinds of basic understandings can really drive your scanning practice to make you be able to operate it better and accomplish more with the technology that we have. The other thing is that it's really just a representation of how important it is to utilize the appropriate frequency for what you're trying to do. Higher frequency has reduced penetration, so if you can't get to the item, it's just not going to work. You're going to have to give up that resolution to at least get an image of the item or the anatomy. Okay. Now, we've already basically brushed on something called impedance, but impedance is something that we represent with the letter Z. And impedance, just like your, in everyday life, if you're impeding traffic, you're resisting it or you're causing a problem there. Well, impedance in the body really refers to our soft tissue, so, or any type of change in tissue impedance or resistance to the movement of your sound waves through it. So if I have a sound wave coming in, and we already talked about how a change in propagation speed of a sound wave would cause a reflection. Well, if we take that one step further, any change in impedance is going to cause a reflection. So impedance really takes into account a number of different things. One of the things it considers is propagation speed, like we talked about, and secondarily, it considers density and stiffness. Now, if we look back to what affects propagation speed, we know that density and stiffness affect propagation speed. Therefore, this is all really kind of one reaction. So with impedance, we're going to, if we had no impedance, and the sound wave was allowed to go through a material with zero impedance, a consistent sound, a consistent propagation speed, consistent density, consistent stiffness, we would get no reflections. And so impedance is important because it provides us with the reflections that create a brightness on our image. So a really great example of impedance would be is if you have, say, a liver, and I'm not an artist, so I always apologize. If I have a liver and it has a portal vein, our portal vein, as you guys know, is covered by Glisson's capsule, and Glisson's capsule is going to have a significant change in propagation speed compared to the tissue in the liver. And so when my sound comes in, if it happens to become incident with our portal vein, because of the significant change in impedance, it is going to cause a big reflection of sound. Now, when that reflection of sound reaches our transducer, that reflection is going to create a significant voltage, right? It reacts with the piezoelectric element. The element converts that sound wave into a voltage, and that high voltage is going to go and it's going to be demonstrated on our image as a significant brightness. Now, if a sound wave comes in and let's say it interacts with the barrier of, let's see, a fatty infiltrate into our liver. Now, that fatty infiltrate may not have such a significant change in density or propagation speed that it would reflect the whole sound wave back. So it would probably reflect something back because it does have a change in impedance, but because the change in impedance was mild, it would not come back with the same kind of intensity that the echo coming back from the portal vein came with. Therefore, when we looked at these two items on an image, my portal vein would be very bright because of that significant change in impedance, whereas my fatty infiltrate would be a subtle echogenicity or subtle brightness because it was a more moderate change in impedance. So we can use impedance to not only give us our image, but we can really use it to assess the density of the tissues that we're looking at. So if we know that something is sending us a big echo, we know that that has a big impedance and that there's been a big change in stiffness or propagation speed. So when you're trying to compare masses and different things, that's important to keep in the back of your mind to help you determine or help you with your differential diagnosis. Now, just because there is a change in impedance, so in this image here, we have sound waves coming in. This we would think of as our barrier between two media. And obviously, we're getting a reflection back here. That would indicate that they're at this barrier, there's a change in impedance. Now, you can see that a great deal of the sound wave was allowed to continue propagation, while as some was reflected. We can refer to this as my reflected intensity coefficient, what percentage is coming back as a reflection, and compare that to my transmitted intensity coefficient. Now, for you guys, that's probably not going to be a huge consideration, but just in visualizing how this works in the body, it's important to remember it's not just one echo coming in, the whole thing being reflected back. It's one echo coming in, part of that, or pardon me, one sound wave coming in, part of that sound wave being reflected back, while the other is allowed to continue penetration. As it continues that penetration, the amplitude is getting more subdued, which is caused by that decibel or attenuation decrease that we know occurs every centimeter of tissue. Now here is an example, a little bit of what I was talking about. Here's a very full screen view of the liver, and you can see this echogenic border here indicates portal vein. That is showing us that there was a significant change in impedance between liver parenchymal tissue and that portal vein capsule. Whereas our IVC is not covered by Glisson's capsule, it just has the normal venous wall layers, and because those the tunica, intima, media, and adventitia don't have as a significant of a change in impedance, you're seeing much more subtle reflection coming off of that IVC. Now, another consideration when you're in your scanning, you're going to get the best echoes back if we do what we call perpendicular incidence. So if I were to have my transducer, so say this is my transducer, and I was able to send out my sound pulse 90 degrees to a border or to a media change with a change in impedance. That is going to promote the most significant or the most pure reflection. So if I hit it at 90 degrees, I should get the greatest echo back. If we pop back to our last image, you could see that was not only was the portal vein a good demonstration of a large change in impedance, it was also a great demonstration of obtaining perpendicular incidence to something to enhance the strength of your returning echo. Now, that's not always going to be possible. You guys know better than anybody how organs are not arranged on vertical and transverse or longitudinal and transverse axes. And even if they are, lots of times we're having to scan around different gases and organs in order to access what we're actually looking at. So the majority of the time, we are actually going to be incinerating tissue from an oblique incidence. Not a huge thing for you all to consider, but it does have an effect on certain artifacts that we may or may not see. So when we have an oblique incidence on a media, such as we have here, when we have a reflected sound wave, it's going to bounce off in a new direction like a ping pong ball. This is going to give us more of a scatter reaction than a true reflection. Now, that which was transmitted then, part of the transmission coefficient, is not going to continue in the exact same trajectory through the media. If the media that it's going into, the new media, media 2, has a slower propagation speed than medium 1, the angle of transmission will be decreased. If propagation speed of media 2 is higher than that of medium 1, it would then have a greater angle than the 45 defined here because of propagation speed. Therefore, your reflections are going to be slightly off out of alignment with where the anatomy really exists. Most of this time, this doesn't affect our imaging too greatly. One thing that it does do is it can cause some mirror imaging artifacts to occur once in a while, and that's something we can touch on a little bit later. But just the idea, perpendicular incidence is going to give you the best, strongest reflection. Oblique, you're going to lose some of that reflection to scatter, and so always, if possible, shoot for perpendicular incidence. Now, the terminology resolution, and it might be simplified for you, but one of the ways I describe it to our students, it is the accuracy of the representation of the anatomy on the image. So we know that there's a certain way that the anatomy exists within the body, and if we are able to represent that anatomy perfectly on our image, that would be perfect resolution. Now, that's never possible, so we're always shooting for the best resolution we can get with all things considered. So there's certain different types of resolution that we are able to try to control or try to optimize to help with our scanning technique and also get us the best images, which for you all will lead to the most accurate diagnosis. So resolution can be defined as axial resolution. Now, axial resolution we touched on earlier, and if this is my image, axial resolution is the ability of a system or an image to differentiate two different closely spaced items front to back on your image. Now, remember how I mentioned that is due to our spatial pulse length. The less space our pulse takes up in area, the more easily that pulse can squeeze in between two different items, bring back information which will then be presented on an image. Okay, so that is our axial resolution, defining items or objects front to back, and is controlled by our spatial pulse length. So for you as practitioners and operators, one of the ways that you can reduce your spatial pulse length to improve your axial resolution is by an increase in frequency. If my spatial pulse length is the space a pulse takes up in space, then by reducing my frequency or making these shorter wavelengths, the spatial pulse length would be reduced, increasing my frequency, which would also increase my axial resolution. So to control axial resolution, improve frequency or increase frequency. Another type of resolution is our lateral resolution, and when we have two items in an image or in anatomy that are separated or side to side, lateral to one another, if we are able to squeeze our sound wave in between those two items and bring back resolution or bring back anatomic information, that anatomic information will appear and cause these two items side by side to appear as separate entities on my image. If I have a very broad sound wave and it is unable to squeeze in between those two objects, it will react with the objects as a whole and it will represent them as one single entity. That's our lateral resolution, is our demonstration of objects side to side accurately on our image. Now, the way, and we haven't talked a lot at all about this yet, the way we control this is with our focus. So as an operator, you're always wanting to find your focus button, and we can show you that if you're not familiar with it, but you want to maintain the focus usually at or just posterior behind the anatomy that you're most concentrated on. Now, if you're say you're scanning a liver, you want to know what's going on in the whole liver, then you would put it at your far field or just posterior to the area you're looking at. A phenomena of ultrasound or pulses is that as they travel, they become more and more broad after a certain narrowing point. That narrowing point is the point that we call our focal area. We are allowed some adjustment of the focal area, which we'll cover more in transducers next week, but we do have to control our focus to keep our beam narrower, and those narrower beams are able to slide in between two different objects, bringing back information and improving our lateral resolution. Temporal, as you know, temporal is time. So one of the things that is very important is that we're trying to scan in real time without a lot of lagging or frame rate recognized. One of the things that we do to address that is that we know when we're talking about that we utilize principle 1, we emit a sound wave and we follow that sound wave by listening time, and then we emit another sound wave. Now, if I emitted a sound wave and I only wanted it to go 3 centimeters into my patient's body, that sound would travel at the propagation speed of soft tissue 3 centimeters into the body. If I was only wanting to see what was in the first 3 centimeters of that body, I would only allow it to have to be gone 13 microseconds per centimeter. Now that is just a value that has been calculated according to the propagation speed of the soft tissue. So if I have propagation speed in soft tissue like we talked about of 1540 meters per second, they utilize that propagation speed to determine that for a sound pulse to travel 1 centimeter to an object and back, it would be gone 13 microseconds. If I want my sound to go 3 centimeters before I send out my new pulse to get a new image, I would have to allow a listening time of 39 microseconds to allow it to travel those 3 centimeters and back. So if I wanted it to go 5 centimeters, I would have to give it more time to get that 5 centimeters and back. In fact, I would have to allow it, let's see, 65 microseconds to go 5 centimeters and back. So if I were to do that, my listening time would be much longer. Now, because basically every pulse is ultimately going to produce an image, if I'm having difficulty with my temporal or my frame rate, and I have a long listening time between pulses, I will have a long time between images. So if I want to decrease the time between where I can see images, what I have to do is decrease the depth of my image so that I get images more rapidly because I have less listening time in the acquisition of those images. So temporal, again, so axial, we're going to control with our frequency, which affects our spatial pulse length. Lateral, we're going to control with our focus, which helps prevent broadening of our beam. Temporal, we're going to address with our depth. And then finally, elevational. Elevational is a little bit more complicated, and how we've talked about ultrasound so far is that it's like one laser thin slice going into the body. Well, when it comes down to it, it's not quite like that. The face of my ultrasound transducer is really going to have a third dimension. And so I'm going to be sending out scan lines not only in this dimension, but in a third dimension as well. Now, because we are basically displaying a 2-dimensional image with 3 dimensions of information, we are going to be basically averaging each of these layers of information to provide our full image. Now, because we're doing that, for example, if I were to see an anechoic cystic structure, an anechoic meaning having no echoes. And yet the depth of my probe allowed me to pick up liver as well. Those livers, that liver feedback would be superimposed over my anechoic area, and we would call that elevational or thickness artifact. So in order to improve our elevational artifact, we want to not only narrow our image like we talked about for our focus, for our lateral resolution, but we also are going to want to narrow our image front to back to prevent that thickness artifact or elevational artifact as well. And you can do that again with your focus. Sorry for my writing here. Okay. All right, we're getting towards the end, so hang in there. We just got a few slides left and we'll get you on your way. The most common modes that you're probably familiar with are like we see up here in the upper right-hand corner. Here's a baby, nice little profile. You're seeing everything in black and white, two-dimensional. We refer to that as our B mode or brightness imaging. Another type of imaging is going to be your M mode or your motion mode. Here you'll see this is an example of motion or M mode. This is most commonly used in echo or with early fetal heart rates or fetal heart rates. Now one of the benefits why we use this in fetal heart rates is because it uses lower energy and promotes less heat development within the fetus. Now the reason we use it in echo is because it detects motion along the whole line of insonation here. So this representation that we're seeing here, this tissue is presenting tissue motion up in this general area. As we go deeper, we're seeing tissue motion here in the right ventricle. Here we're seeing tissue motion through the left mitral valve, and then here we're going to see tissue motion in the posterior wall. So it's showing you tissue motion all the way through along the length of that line. That is our M mode. This is a quantifiable analysis of tissue motion. I can measure and get a quantification of how many beats per minute we're looking at here. I can also utilize this to measure the thickness of, say, this posterior wall of myocardium. I can actually measure off of the M mode to determine that thickness. So this allows for quantification of information. Doppler, color Doppler. Color Doppler, it is actually assessing for any sort of movement within the body, and whenever it's detecting movement within the body or a Doppler shift, as we'll talk about more later, it applies or assigns a color. So here we see, this is very common with our vascular scanning. Spectral is utilization of that same sort of Doppler information, and yet rather than applying it or demonstrating it as a color, it basically graphs it. So it uses our x-axis as time, our y-axis as velocity, and for every moment in time, it will put a demonstration of all the velocities picked up in one particular gated area and represent the variety of velocities and the changes in velocities of blood flow over time. And then, as you know, people are excited and invested in volume imaging these days. 3 or 4D volume imaging, this would be as an example of a 3D image. It's the collection of multiple 2D images in a volume, and we're able to then, in post-processing, scan through that image. The difference between 3D and 4D is that 4D is 3D during live time. So you could actually watch this image that we see here. We could be watching that baby move. That would be considered a 4D. From your perspective, as you utilize ultrasound more and more, most point-of-care ultrasound equipments are not going to have 3 or 4D options. Through the Helmsley grant, GBC has purchased some equipment with these options, so if physicians need additional training or are going to have something like this in their office, that's something we can try and help you with. But as the more and more you scan with ultrasound, it seems like people become so comfortable looking at things in 2 dimensions that the 3rd dimension really isn't as helpful as you might imagine it would be. The Doppler effect, as I mentioned, we are able to apply that overlying color to demonstrate motion, or that motion on our spectral analysis, all because of the Doppler effect. And the Doppler effect is something everybody's pretty familiar with. You know, this is really common with radar guns. If you're speeding towards a policeman, they utilize the Doppler effect to determine how fast your velocity is. We use it very similarly. So the basic idea behind Doppler effect is if we're sending out a sound wave, and that sound wave is coming towards something and eventually crashes into something that has motion in the opposite direction, the reflected echo is going to have a higher frequency than the fundamental or the original echo. So maybe to say that just a little bit clearer, or to demonstrate it a little bit clearer, if we have a sound wave coming and it encounters something that's coming straight at it, and they have a collision, it is going to create an echo, but that echo will have a higher frequency than, or more cycles per second than the initial sound wave. We call that a positive Doppler shift. If we have a sound wave going and we have an object moving away from it, that sound wave is going to have to travel to catch up with that sound wave. Because it had to travel to catch up with it before it interacted, it's going to end up producing a sound wave with a lesser frequency, or pardon me, an echo with a lesser frequency. We would call that a negative Doppler shift. Now, depending on how big the positive Doppler shift or how big the negative Doppler shift is, that information can be applied to equations to determine the exact frequency, or excuse me, the exact velocity in which that object was moving. Now, all of our color Dopplers and our spectral Dopplers are based off of these Doppler shifts. Here's an example of a Doppler shift. So, and we'll get into this in a little bit more detail in future lectures, but this box here is showing color Doppler applied basically over the top of a B mode image back here. So this B mode image is being created according to principle 1 that we talked about. And then we're telling our equipment, I want to obtain color Doppler information as well. So this color Doppler image, it's sending out scan lines in this direction with this parallelogram box that we have created here. Now, as the operator, you or anybody else operating this equipment could shift or steer the box the other direction. Now, when I have sound that is, or pardon me, when I have motion that is coming toward the scan lines, here you see they're going to intersect because they're moving toward one another. This would give me a positive Doppler shift. If I have my scan lines going perpendicular, as I do in this box, my sound waves are my motion of my blood flow is going to bump into them, but it's neither really going toward or away. Because we don't have it going toward or away, those clashes aren't as significant, and we don't get the same kind of Doppler shifts that we otherwise would get with a steered box. Therefore, you see this lack of color filling in here. And as the operator, you would either want to get the vessel to go across your screen as an angle, or you would want to steer your color box in a new direction to provide those collisions that are essential to creating a Doppler shift and providing color flow information. Now, whenever you're doing color Doppler, you will see something that looks like this scale here on your screen. Now, anything that is represented in this particular scale, anything that's represented above this baseline would represent a positive Doppler shift. Anything below this baseline would represent a negative Doppler shift. So this would be running away from my scan line. This would be running towards my scan line. Now, a common misunderstanding is that our equipment naturally just applies red to arteries and blue to veins, and that's not the case at all. It's under the operator's control to make arteries look red and veins look blue, and we have to steer our Doppler angles, as well as invert or adjust our color scale to ensure that we can represent our arteries with red, our veins with blue, and assess exactly how blood flow is moving. This can become very important if you're looking at like the carotid area, and some patients that develop a subclavian steal will develop retrograde flow in the vertebral artery. It's really important that we don't just put color on an artery and assume that that color, say for the vertebral, assume that that color or the blood flow is going towards the head. We always need to take all of the hints and clues to make sure that it truly is going the direction that we're expecting it to. So make sure you're really familiar with this. Sometimes it can take a lot of practice, and sometimes it comes very easily to people. But it's something to definitely be familiar with if you're new to ultrasound. Now on our right image here is just, I'll briefly speak about this, but you'll see that we have an arterial Doppler, or an artery filled with red blood flow here. We can see that our scale is showing that the red is above the line, meaning that the red is having a positive Doppler shift. That positive Doppler shift is coming because blood is moving towards the left of this image, which in this case would be the patient's head, and it's colliding with that scan line in a head-on in a collision. Now, if it were to be running away from that scan line, it would have a negative Doppler shift and it would be assigned a blue color. So because it's red, because our red is a positive Doppler shift, we can tell that our blood flow is going this direction. Now, this happens to be the same vessel that we're looking at here and here. You'll notice that we're getting some blue in there. Now, oftentimes that could mean turbulence. It could mean a number of different things. It could be there's a stenosis, something significant. In this case, what it simply means is that our scale is not set large enough. So if I have my scale, or I'm telling my machine only read to, say, this is just an example, 23 centimeters per second, and if my blood flow is going faster than 23 centimeters per second, it will start representing anything beyond this level as blue, and we call that we call that aliasing or wraparound. And you'll see that it's true here in this color flow, here again, and then you even notice it in the spectral Doppler as we're getting velocities above what the technologist has the scale set at. We're getting this wraparound, so the peak is being represented below the baseline. So something to be familiar with. We can go into this more in depth. This might be something hands-on wise you want to practice with a lot when Erica comes out to your site, because it does take some work if it's not something you're very familiar with. Okay, in summary, I know I've kept you over an hour, so I'm going to let you read through these on your own. Please, if you have any questions, let me know. I hope that you are finding how this information will be useful in your scanning. Oftentimes, I think in training physicians, we put you right into into the fire and don't give you all of the tools to be successful. So hopefully these tools will make you not just successful, but kind of exemplary at what you're doing here with your point of care ultrasound work. So thanks for joining us. We'll see you next week.